Hello everyone, our group had chosen field of study versus occupation dataset for our study. Today, we will introduce the chosen topic using the rapid minor application. Our team members consist of AHMAD Danial bin AZMI, AMISHA ADILA binti IMRANSYAH, Rayhaan bin Amran, MOHAMMAD AIMAN bin MOHAMMAD SALLEHUDDIN, and me myself NURUL NATASHA NABILA binti BAHARUM. Rapid Miner is one of the most popular machine learning communities and data analytics environments in the market. It is an intelligence framework that offers AI solutions to positively impact businesses. Rapid Miner serves as a data science software background for data extraction, data construction, deep learning, machine learning, and descriptive analytics. It also offers a free trial allowing users to access its capabilities. A classifier can analyze patterns in the data to predict the likelihood of an individual changing occupation. This dataset may include variables such as likely to change occupation, current occupation, age, and gender. For the data features, the dataset contains the following attributes: age, gender, field of study, current occupation, years of experience, education level, industry growth rate, job satisfaction, work-life balance, job opportunity, salary satisfaction, skills gap, family influence, mentorship available, certification, freelancing experience, geographic mobility, professional networks, career change event, technology adoptions, and likely to change occupation. Purpose of the study is to understand the factors that influence career transitions, that is essential for workforce planning, career counseling, and industry analysis. The study utilizes the field of study versus occupation dataset to examine how academic background, job experience, and other demographic factors contribute to career changes. The dataset contains over 30,000 records with 22 attributes encompassing variables such as job satisfaction, skills gap, industry growth, and professional background. The target variable, likely to change occupations, enables predictive analysis of career shifts. To conclude, this dataset serves as a valuable resource for understanding career transitions through data-driven analysis by examining the relationships between current occupation, field of studies, provides insights into workforce dynamics and career decision-making processes.
Assalamualaikum and hi, my name is AMISHA ADILA binti IMRANSYAH and I will be explaining about the extract, transform and load process in Rapid Miner in our project. The ETL process in Rapid Miner involves several key operators that help extract, transform and load the data efficiently. And these operators include retrieve, which first loads the data set for processing. Next, we have filter example, which selects specific data based on defined criteria. Next, we have set role, which assign role to key attribute for analysis. And next, we have select attribute, which remove redundant or unnecessary feature. Now, let's talk about the process that we have done for our project. As you can see on the figure, we have chosen the retrieve operator, which first loads the data set and relevant attribute, such as education. And they are selected for proper extraction, and that is confirmed by a green indicator. Next, during transformation, new attributes such as probability of career change are created using the generate attribute operator, and the set role operator defines the role of each attribute. Next, we have chosen numerical to polynomial operator because it converts numerical data into categories. And the filter example operator focuses on specific groups like ages 25 to 40. That is the age range that me and my group have decided to pick for our project. And next, we have the replace operator, which first standardize attribute values and select attribute operator after refining the data. The store operator saves it and confirmed by another green indicator. And finally, the most relevant attribute are selected, ensuring that the data set is clean, ready, and optimized for analysis, which next will be modeling.
Assalamualaikum warahmatullahi wabarakatuh, and a very good day to all of you. My name is AMAN bin SALLEHUDDIN, and today I will be presenting the split data modeling method that we used in our Rapid Miner dataset process. Let's begin with split data. What is split data? Well, basically split data is a technique used to divide datasets into different subsets. It helps in evaluating the performance of a machine learning model and selecting the most effective outcome. it can be used for various purposes such as training, testing different machine learning models, comparing different parameters, or also performing cross-validation. For the split data processing that we employed in our RapidMiner assignment itself, we use these following steps as you can see in the slides. First of all, retrieve a clean data set of field study versus occupation, which is our given data set, using the retrieve operator. Next, we use the multiply operator to create an independent copy of the data set by connecting the input port to the output port. Next, the multiply operator is then connected to the split data operator, which helps divide the data set into a specific subset, which in this case we are using 70 to 30 ratio. Next, the split data operator is then linked to 4 machine learning models, which in our case, as you can see here, consists of RF, KNN, NB, and also GBT. RF stands for random forest, KNN is KNN, and NB is naive Bayes. And aside from these 4 models, we also use other machine learning models, including GLM, Generalized Linear Model, Decision Tree, Neural Network, and also Deep Learning. However, these other models' accuracy was not up to par, as the accuracy that we are looking for is above 70 to 90. Therefore, these models did not make the cut, and instead we went with the models that are appearing in the slides. So, these models are connected to the applied model and performance classification operators, which helps us evaluate the accuracy of the result. And once the data is split, the algorithm runs to assess the accuracy of each model, and this process is repeated to obtain consistent result. That is all from me. Talking about the accuracy and whatnot will be my friend Rayhaan bin Amran. Thank you very much.
Hello and Assalamualaikum everyone. My name is AHMAD bin AZMI and I'll be presenting on cross-validation for our dataset. Today I'll be walking you through a process of evaluating predictive models using cross-validation. But first, what is cross-validation? Cross-validation is a crucial technique in machine learning used to assess the performance and generalization ability of a model on unseen data. And so instead of simply training a model on all available data and then testing it on a separate held out set, cross-validation strategically partitions the data into multiple subsets for training and validation. This helps us to obtain a more robust estimate of how well the model will perform in real-world scenarios. So without further ado, let's walk through the process depicted in the diagram beside me. So first, the process begins by retrieving a clean dataset ready for model training and evaluation. Then it goes through a attribute selection operator, which is used to select the essential features relevant to the prediction task. These steps ensure that the model focuses on the most important variables, potentially improving performance and reducing complexity. Then there's the set role operator, which allows roles to be assigned to attributes, specifying whether they will be used as predictors or as the target variable. Then there's also the data multiplication, which allows the data to be duplicated and branched out to multiple cross-validation operators that contains a specific model in each of them. The models are naive Bayes, decision tree, and random forest. And all of the cross-validation operators lead to the append operator, which merges the results to make an easier comparison. The core of the process involves k-fold cross-validation. So how does it work? The dataset is divided into k equal size folds or subset. Then the model is trained k times. In each iteration, k1 folds are used for training and the remaining fold is used for testing. The performance is measured on each test fold and the results are averaged to provide an overall performance estimate. Moving on to the model and results. In this process, there are 3 different models that is evaluated, which is, as mentioned before, naive Bayes, decision tree, and random forest. The diagram shows the cross-validation being performed separately for each model. We see the result for both K10 and K20. At K10, we have a similar result on naive Bayes and decision tree, which is 69 68.32%, while random forest is slightly a little bit less with 69.21%. For K2 is also similar, which is naive Bayes and decision tree 69.32%, and random forest being a little bit lower than K10, which is 68.18%. Interestingly, for K10, all three models achieve very similar performance, around 69%. When we increase K to 20, we observe a slight decrease in the performance of the random forest model, while the naive Bayes and decision tree maintain their performance. This could potentially suggest that the random forest model might be slightly more susceptible to overfitting with smaller training sets, as each fold has less data when K is larger. However, the difference are relatively small, and we might need further investigation or more data to draw a definitive conclusion. But these three models are best suited to use in our cross-validation process, as it produces the best accuracy results. We didn't use gradient boosted tree model that is used in our split data process, because even though it gave the best result for split data, it didn't do the same for K-folds. In fact, it did a lot worse compared to the other models. In conclusion, the process demonstrates the importance of cross-validation in evaluating and comparing machine learning models. By systematically partitioning the data and evaluating performance across multiple folds, we gain a more robust understanding of how these models are likely to perform on unseen data. In this particular case, while all three models showed similar performance, the cross-validation process allowed us to observe subtle differences in their behavior when varying the number of folds. That is all from me and K-fold presentation. Thank you very much.
Assalamualaikum and good day. I am Rayhaan by Amran, the fifth presenter of the group, and now I'll be talking about the model performance analysis. So for the first one, as you can see on the table, our calculation shows that the 70-30 split has the highest average, which is 68.9%, compared to the 90-10, which only gives 66.65%, and the 80-20, which only gives 66.82%, suggesting that the split ratio of 70-30 gives better overall performance. This could be due to a more balanced contribution between the training and test data, optimizing the outcome of the split ratio. It's also possible that increasing the component beyond 70% leads to diminishing return, where further increases don't add value or even hinder the performance. Given that 70-30 consistently yields the highest average and aligns with these considerations, we chose this split as the optimal balance for our analysis. So as you can see, a graph was used to highlight the performance of several machine learning models on the field of study versus occupation data set. The labels were set to determine the probability of career change in relation to an individual's education level from 5 selected careers. The results are as follows. For the first one, naive Bayes performed with the accuracy of 29.29%. And some reason we think it performed poorly is because simplistic assumption. Naive Bayes assume that all features are conditionally independent, which is unrealistic for career change prediction, where factors such as job security, salary and education level are highly correlated. And then maybe naive Bayes struggle with non-linearity. Career change is influenced by complex interaction between variables, which naive Bayes fails to capture effectively. And then maybe there's some class imbalance issues, like if the data contains more no than yes cases for career change, naive Bayes tends to favor the dominant class, leading to a lower accuracy. And then the second model we use for the machine learning is K nearest neighbor or KNN, which yields 59.64%, and it performed moderately because KNN works well with cluster. KNN is effective when there are distinct patterns in dataset, such as strong correlation between work-life balance, geographic mobility and career change. And then KNN also struggle with high dimensionality challenges. Since the dataset contains multiple attributes, KNN struggles with dimensionality, where distance calculation becomes less meaningful. And then there's also the scaling of sensitivity. Unequal scaling of numerical versus categorical attributes may have affected some of KNN's performance. For the third machine learning model we used was random forest, which yield 86.17% of accuracy. Some reason we think it performed well is random forest effectively captures between the relationship between multiple attributes such as job satisfaction, career growth and salary. And then random forest also prioritizes key attributes such as work-life balance and geographic mobility while ignoring less relevant ones. And then with an ensemble of decision trees, random forest generalizes well to unseen data, which improves its accuracy. And then for the details that we use, 100 trees with a depth of 10 to give a balance of performance and computational efficiency. And then for the fourth and best performing model, we have gradient boosted tree, which gave the result of 97.26%. Some reason we think this happens is iterative boosting, where gradient boosted tree build tree sequentially, improving weak prediction and refining the model at each step. And then GBT is highly effective in handling non-linear relationship between education level, job satisfaction and career change likelihood. And then it also focuses more on harder to predict samples, reducing bias toward dominant classes. And some details of it is we use 250 trees with a depth of 10, which optimize the performance through fine-tuning. And then the key insight that we learned from the research is career change, interest and education level were the most influential predictors of occupational transition. In conclusion, this data set provides a valuable opportunity to explore career transitions using machine learning. It enables predictive modeling for maybe human resource analytics, career counseling, industry trends and job markets insight. And by leveraging the data we have gathered, we can better understand factors influencing job changes and support informed career decision. That is all from us. Thank you for listening.